So welcome back, everyone. Welcome back to this class. Yesterday, very happy you were able to accomplish your first online quiz. But if you think about it, it's not really a quiz, it's an online homework, but I mean timed. So because there was no supervised, no proctoring. So anyways, well, I'm pretty happy with the outcome. I'll go through the reading of the questions first, then I will go through the solution. Okay. So if you have any question at any time that is relevant, please go ahead. So I was saying that the first question was CR factorization. Well, it's quite close to the question we've seen on the homework one, but here the matrix is a little bit. I'll come back to your question, Hassan. So the matrix is a little bit more difficult to handle. So you can see here that, for example, column 3 would obtain by combination of columns 1 and 2, or that you could say that easily that column 1 plus column 3 divided by 2 give directly column 2. Okay. So basically, I will read the solution. Now, the LU elimination, there was a small thing, is that this is not A equals to LU. It's not A equals to LU. It's PA equals LU. What is P? We'll see it later on. Of course, P, we've seen it in the class. It's a permutation matrix, which is not the identity matrix, okay? Because you base your permutation or the reordering of your rows based on the first entries in the first columns, okay? So the next question is the spectral vectorization. And here I'm providing a small, beautiful matrix, which is symmetric, which we can apply the spectral vectorization. And we need to compute the eigenvalues, the eigenvectors, and to write S as a factorization, using a spectral vectorization. Last question is a kind of minimization problem. Of course, it's, as you see in the title of the question, it's based on positive definite matrices. Where does the positivity of matrix happen here? Of course, in question B, because we need to compute the Hessian matrix and verify its positivity. So let me go through the quiz solution. Inshallah, if you have any questions, it's very important to me that everyone resets its odometer and realizes now he starts to work more serious. So I'll go through the solution. I will zoom in. Well, it's a handwritten solution. I didn't have time to type it. It's a lot of work. As you know, yesterday I spent more than 2 hours also grading your quizzes. So Hassan, for your quiz, for the average is 23. 30. How much is that? It was 71%. Yeah, and about 28 over. Let me see it again. Okay. Yeah. The average was 28.15 and 70% over 40. Okay. Yes. Okay.
28.15.
Yes. Yeah, 28.15. Is it Tamer or Abdulaziz? Okay. Yes, Tamer, go ahead, please.
Doctor, regarding question 1, there is another way.
Yeah, there are many ways to do it, but I will go to the. Okay. There are 2 ways to do it, in fact. But okay, so I read my solution. Of course, I agreed that I gave full mark to both answers. So question 1. So this is your the question, and here I'm saying that you can notice directly using your reduction, of course, that C2 is equal to 1/2 of C1 plus C3. Otherwise, you can also write directly that I think C1, in fact, if you take it, it's 2C2 equals C1 plus C3, which is exactly the same. Yani, one can write that C3 is equal to minus C1 plus 2C2. Okay? So basically, it gives a different second column. You will place the second column instead of the third column. And instead of having this R, I obtain it, you'll have a different one. So basically, for those who did that, you will get something of this kind. Get A, which is 132, of course, 323, and you will get the matrix here, of course, 1, 0, minus 1. Here you get 0, 1, 2. Okay, am I right, guys? So you get basically the same answer. Okay, so there are different, as I said, different CR factorization. Yes, please go ahead.
Can you use a different color because we can't see anything? The contrast is bad. Maybe.
Which color, Fanny?
Red will be better.
Black, red. Red. Okay. So I'll zoom on this one. So is it better this way? Okay. So hopefully it's much better this way. So from now on, I'll write in black or red. Okay. So any question on the first problem, Shabab? So according to the item analysis, I mean, the average on that question was 7.8, and I expected. I mean, I've seen the answer of Abdurrahman. It's right on question 1. So basically, it's around 8/10. So mostly, I think 2 or 3 students, 2 or 3 of you, they didn't notice that the three columns were independent, were dependent. I mean, they consider that they are independent. So be careful, guys. So that was a pretty fair question, or let's say easy question. I'll move on to question 2, if you allow. Now here, you need to notice that it's not an A equals LU factorization or elimination that we are asking for. We are asking for a PA equals LU factorization. What is P? Of course, P is a permutation matrix. And of course, there are many possible answers here, many possible permutations, but we said that the best algorithms are those who reorder the matrix in terms of the greatest entries in the first column. So basically, my aim is to put 4 first, then 2, then 1, if you see, okay? So that's why I needed what? The second row needs to come in first row, as you see in A. Then the third row, that's why I'm putting here, comes in second position. Then the first row is placed in third position, okay? So PA, this way, if you do the math, guys, if you multiply this P, 0, 1, 0, 0, 0, 1, 1, 0, 0 by your A, you get 4, 0, 1, 2, 1, 1, 1, 2, 2, okay? Okay, so this is the way the algorithm would work. Otherwise, there is another possibility or an acceptable answer. I accept it also, that places the third row or the second row in first position, basically, and you stop there and you continue. So we have slightly different, so you get a slightly different. Okay, those, Hassan, as Hassan said, those who said A equals LU, well, you get a penalty because this is not the question. So those who did A equals LU, they got 8 out of 10, okay? And if they did it right, of course, because they needed to use a permutation matrix. I think it's pretty fair. Right. Now, how to get the columns in L? Well, you know this is basically the elimination. So you need these kind of pivots. So the first one would be 2 over 4. The second one here will be 1 over 4. So basically you get this first column, 1, 1/2, 1 over 4. If you do the reduction here based on these pivots, you get this new matrix. Okay? And this item now needs to become 0. So the next pivot you're going to use is 2 over 1. So L32 is this entry 2 over 1. So basically you place the 2 here. Okay? The L contains all ones in the diagonal. And of course, if you do the reduction now, you continue to obtain U. So this is the U I obtain. Of course, if you work it slightly differently, okay, you obtain a different LNU. Okay. Right. So those who wrote A equals LU, the answer is not that wrong, but it's not the A equals LU. It's not the optimized version of the elimination. Okay. Hopefully, it's clear for everyone.
I have a question.
Okay. Firas, go ahead, please.
Really, do we have to rearrange the permutation matrix if we saw these? We have, let's say, the second pivot it is less than the row before it or after it.
Ideally, yes, you have to reorder ideally, you have to reorder the rows this way, in terms of on decreasing order of first entries in the first columns. So I place it here 4, 2, 1. You see, of course, you can choose arbitrarily. Of course, you can choose arbitrarily in case of ties. In case you have a tie, okay, you can choose arbitrarily. But we said that the best, and it's written in the lecture notes, that the best algorithms are those who reorder these lines. In fact, if you notice when we run also the Python code, the library automatically reordered the rows, and if you checked, you would have understood that this is how it works. And we checked it together, of course, when we run the code. We said, look here. I remember I said, look here. They performed the permutation. This is how they did the permutation.
Okay. My question, second column. After I'm finishing, I finish the elimination the first, I go to the second column. If I saw that I can rearrange the matrix, do I go for it?
What do you mean? Did you? Where are you? You are here. You are at 0, 1, 1/2, 2, 7, 4.
Yes, I'm here. So I saw 2 is greater.
You don't. Okay. No, I don't advise. Permutation is used there once only. Okay. Because otherwise, basically, you are inserting another permutation matrix, and you don't get the right answer. Right. So S, now question 3, can I move forward, Firas? Are you okay with this?
Yes, I'm fine.
Okay. So now here, of course, I didn't take a complicated matrix. I want the matrix to be very illustrative and allow you to get very easy eigenvectors and very easy eigenvalues. Okay. Still, with that, there was a small trick, of course, for those. This is where I want to pick you up, Shabab. I want to pick you on the things that you need to focus on, the details that would make you lose a lot of time, waste a lot of time if you're running the computation. So here the matrix is symmetric, basically, so we can perform the spectral vectorization. Beautiful. So let's find the lambdas. Well, I think everyone understood that we need to solve determinant of S minus lambda I equals 0. You have a beautiful determinant, 2 minus lambda, 1, 1, 2 minus lambda. You have a beautiful second degree equation you need to solve. Okay? It's lambda squared minus 4 lambda plus 3 equals 0. Everyone found these answers. Lambda equals 1, lambda equals 3. Beautiful. No question on that. So, now, when you insert these eigenvalues, you are supposed to find the corresponding eigenvectors. So the first eigenvector solves SV1 equals lambda 1 V1. So basically, you're using, if I write the components of V1 as A1 V1, I do the product here should be equal to A1 V1. So basically, I'm solving Q A1 plus B1 equals A1, and A1 plus 2B1 equals B1, which reduces to a single equation. A1 plus B1 equals 0, يعني B1 is equal to minus A1. Okay, of course, يعني you can the only thing you have to verify is that it's this relation. Now, if you solve with the second lambda, sorry for the blurry thing, Shabab, I'll zoom on a little bit. So for lambda 2 equals 3, you get a second relation which writes A2 equals B2. Okay. Right. Now, what do you need? You need to verify that the two vectors, and few of you did, honestly, but I skipped it honestly. يعني orthogonality يا شباب. Here I didn't penalize any one of this, and it doesn't happen all the time that two vectors obtain a direct orthogonal, and we've seen it with the example we run in class. So orthogonality, you need to make sure here that A1 times A2, so the Cartesian product here, or the dot product of the two vectors gives a 0. So A1 times A2 minus A1 2 equals 0. Of course, this works automatically here because it gives you already 0. Okay? So whatever are the values of A1 and A2 is going to work. But it's not the case all the time, and we said that we had to be careful. Here, I consider that it's okay, it's obvious. Now, how to find the components, the correct components of V1 and V2? Most of you, or all of you, let me say, chose the most obvious values. They said A1 and A2 equals 1, and I found these two beautiful vectors. Okay? But at the same time, most of you forgot that these two vectors, once obtained, need to be normed. Yani they have unit norms. And we said it many times, if they don't have unit norms, even they are orthogonal, you don't get the spectral factorization correct. Okay, يعني what is unit norm? يعني length of each one of the vectors should be how much? It should be equal to 1. And these two vectors, of course, you see that their norms is not equal to 1, and you've seen it, in fact, in calculus 3. I'm pretty sure everyone took calculus 3. So you need to divide by the norm of each one of the vectors, which is root of 2, to get unit norms. So I've named here two new vectors, u1 and u2, which are orthogonal and have unit length, yani 1 unit length, so they are orthonormal. Okay? Type here, what happened if you didn't do that? I gave you 8 over 10 if you didn't do if you didn't divide by the if you didn't use the new vectors. Because whatever happens, if you don't do that, you don't get the right answer and you don't get the right S and Q. Okay? So what is Q? Q is the matrix here, which has in its columns the two eigenvectors which are orthogonal and have unit length. Okay? So this is 1 over root of 2 times U1 times V1, and this is 1 over root of 2 times V2, and you put this is Q and here QT. Some of you, they noticed that it didn't match there, so they wrote a totally different Q here. They wrote 1/2 minus half to match, to make the computation correct. Of course, it doesn't work like this. Q is and QT should be related. One of these transpose of the other. Okay, so those who didn't use the divide by the unit norm, they got 2S in fact. And some of you, they already noticed that they got 2S, but they didn't think about it. Okay, of course, the matrix lambda, which counts between, takes the diagonal matrix that takes the eigenvectors. Of course, in the order of appearance of the eigenvectors when you place the Qs. Of course, is that okay, guys? And this is the verification. Yes, Abdullah, go ahead.
Doctor, the value of square root of 2, you found it by calculating the magnitude of the vector?
Yeah, the length of the vector, magnitude of the vector, is just 1 plus 1.
Okay, thank you.
It's just a Cartesian distance, as you remember from 2, 1. Abdulaziz.
Doctor, if I forget to have the 2 unit vector, so I will get 8 out of 10 from the question, right?
Yes. What else did you forget, Abdulaziz? Tell me.
What else did I forget?
Yeah.
It is only the unit vectors. That 1
How
over
much did I give you? How much did I give you?
7 out of 10.
I gave you. Okay, I will change it. Okay. Fine.
Thank you.
Okay, can I move forward? Should I have any question? Other question on this? Okay, طيب. So let me proceed. What is left? Left on the last question. Am I right? Okay, question four. And here, صراحة شباب, let me be honest with you. I try not to be very sarcastic. Let me try just to be funny. Of course, I've seen many things. And this is the question where I had the worst results in terms of average. For some reason, I don't know, this was supposed to be obvious. But we said to find the minimum, what do we need to verify? And it was very clear. Huh? We need to verify what we call ايش سميناهم شباب? Anyone wants to type? ايش سميناهم? First order condition, يعني conditions given by the first order partial derivatives. يعني first partial derivatives. We need 4x minus 4y equals 0, and at the same time 2x squared minus x plus 2y equals 0 to have this critical point. Okay, now in question A, they need to find all points. How many points are there here? There are 3 points. Some gave 1, some gave 2. Few of you found the 3 points. How do we find the 3 points? Okay, let me explain. The first equation here, the first partial derivative of f with respect to x gives 4x y minus y equals 0. So if you factor by y, it's y times 4x minus 1. So either y equals 0 or x equals 1 over 4. Yani we have how many choices here? Shabab, how many choices do we have? We have 2 choices. Yani ya imma y is 0 or x equals 1 over 4. Hello? I'm kind of drawing on the margin here, kind of a decision tree. Right. If I go to the next question, I'm going to plug these values. That's it. So if y equals 0, I have a new equation, which is 2x squared minus x equals 0. I factorize, I get imma x equals 0. So in this case, I have 2 nodes. With x equals 0, I get the first point, which is 0, 0. Okay? Hello? When 2x minus 1 equals 0, I get another point, which is half 0. X is half, and y is already a 0. Okay? So here I have how many points? I have already 2 points. Okay, but I didn't finish yet. On the other side of my decision tree, I branched with x equals 1 over 4. When I plug the 1 over 4, I have 2 times 1 over 16. 1 over 8. Minus 1 over 4. This is like minus 1 over 8. Am I right? Plus 2y equals 0, yani 2y equals 1 over 8, which means y equals 1 over 16, which means you have a new point. I didn't find this point before. It might happen that you rediscover the same point the second time, but here it's not the case, so it's 1 over 4 over 16. If you found this point, by the way, while it is the most interesting point. Okay. Now, any question on the first question? Any remark, observation on A here in 4? Okay, so there are 3 points. Okay, if you missed 1 point, I gave you 4 out of 5. But if you can't, you got something else. Okay, it's either 3 or 4 depending on your work. If you didn't show your work, of course you get a penalty. Now in B, what do I need to compute? I need to compute the second derivatives, the second partial derivatives, and to find this beautiful Hn matrix which contains these derivatives. So the H here is 4y, 4x minus 1, 4x minus 1, 2. Okay, and you see it depends on x and y here. It's not a constant matrix like you've seen in the previous questions. Hello? And in purpose, in fact, at the demand of one of you, or some of you, I already uploaded the problem set from sections 1.5, 1.6, 1.7. So you can see some application and you could practice. Anyways, so now I need to study this matrix A at each one of these points. So if I take 0, 0, I have a matrix which is 0, -1, -1, 2. I was surprised because most of you, they went directly verifying the whole determinant. No, you need to verify the leading determinants. The first determinant is this one. Okay, and there is a whole picture, a whole figure in the lecture slides that details this. Okay, so the first leading determinant is D1, 0. It's okay, we can proceed because 0 could be considered as a positive number. But the next, the determinant here is -1. So it's less than 0, so this point is rejected as sum of Euro. It cannot be considered as a minimum. Okay, it's kind of a saddle point. Now, at half 0, the second point, if you plug half and 0 in H, you get a new matrix which is 0, 1, 1, 2, which is just, quite close to the one obtained at 0, 0. D1 is 0 again, and D2 is again -1. So the whole determinant is again -1, is less than 0. So these 2 points are rejected. There is no way 0, 0 and half and 0 could be considered as minimum. Okay, so those who answered that because they only found these points or they only found 1 point and said, oh, it's obviously minimum, is completely wrong. Now, the last point which was found was 1/4, 1/16. And if you plug these numbers in H, you get this beautiful matrix, which is positive definite. You have a first entry here, D1, which is 1/4, and the second entry, which is 2, which gives you a determinant of 1/2. Now, you need to verify all leading determinants to conclude that's positive definite. It could happen that the first entry is negative, but luckily you get a determinant which is positive. No, the matrix is not positive definite in that case. Here is the case where the matrix is strictly positive definite, and of course we can conclude that 1/4, 1/16 is a minimum. فهمنا شباب? Of course, if you answer this way, you get a full grade. Of course, 10 out of 10. Otherwise, you get penalties for missing points, for not computing all leading determinants and stuff like this. Is that clear for everyone, Shabab? Okay, so I'm showing you guys. We are taking time from material because we consider it's very important to understand how things should be written and things should work. Okay, hopefully, so I graded everyone except those Abdurrahman. I'll just do it around noon, inshallah, and everyone would have received his grade, which would be a little bit, inshallah, above 71 or 60%. Abdulaziz, go ahead, please.
Doctor, could you please upload the solution? Thank you.
Yes, of course. I already uploaded here, and I will upload it on welcome. Okay. I noticed that today I read the messages. I'm sorry for that. I told you I have been 3 days without email, so I've seen that 2 of you tried to watch the lecture videos, session 7 and 8. I tried them all, and they were working. I will put them. I'll verify again the message. I'll send it again. Okay, just to come back with this observation. So I'll start sharing this document. Now I'll share another document with you. Okay. Which one I will share with you. So let me share with you something. First of all, let me share the application screen for my. Okay, what is the last thing we've seen together, Shabab? If you remember. Last thing we've seen, Shabab? SVD, صح? Singular value and vector decomposition. Okay, so the last we're taking here, I'll take like 10 minutes of Python. Okay, and I'll upload the file. The last thing we've seen is how to work on non-symmetric matrices, okay, and find the singular values and singular vectors, and how we can perform this beautiful factorization, which writes, what does it write? It writes a given matrix A as U times sigma capital times VT, okay? So here, Shabab, I wrote a piece of code that does this on the exactly the example that is given in the lecture slides, which is 3045, a small matrix which, as you could observe, is not symmetric. So in a way, we could perform a symmetric a spectral factorization here, as you know. Spectral factorization works for symmetric matrices. This is not the symmetric matrix. Right. So what do we need from that? We said to work correctly, what do we need? We need AT and A. So first of all, I'm writing the code here. I'll go through the code. I need the transpose of A. So as you see, when I call transpose here, I do the obtain the transpose of A. I'm calling it AT. So AT is transpose of A. Okay. And I'm writing the new matrix B, which is AT dot A. So AT times A. I'm bombing the dot product or the cross product, the dot product of two matrices. So I define two matrices, B and C. First one, B, is AT times A. I'm writing the combined part here, ATA, and this is A times AT. Of course, the two matrices you could obtain here are symmetric. Whatever is the matrix, you're going to obtain two symmetric matrices, and I'm going to display them. When I use the command print, as you know, I'm going to display them just to check that everything is okay. Okay. Now, as you've seen before with the LU elimination or spectral factorization, I'm asking it to compute my eigenvectors and eigenvalues here. First of all, for B, yani for ATA, compute the eigenvalues W and V are the eigenvectors. I'm going to display them just for curiosity. Here, I'm going to display the eigenvalues of B, the eigenvectors of B. And I'm going to transpose the matrix of eigenvectors. Why? Because in the mathematical work or analysis, we said that we're using the matrix Q or V that takes the eigenvectors in columns. Here, when the output is provided by the NumPy library, is given where the eigenvectors are provided in rows. So I need to transpose it. So I'm going to verify that I have the correct thing, and the eigenvectors are, when I do the dot product, what am I supposed to find, Abdulaziz? PTV. Let's see if you are following. Or anyone else. Firas, what am I supposed to find?
The matrix.
No.
I'm verifying exactly. Thank you. Verifying orthogonality of the eigenvectors, so I'm multiplying VT by V, and it's supposed to give me, as you said, the identity matrix. Okay? And here, NumPy here does this automatically. It gives you beautiful, which we couldn't have by hand for the unit length. Here, the NumPy does it automatically. So it gives you orthonormal eigenvectors. Okay. So I'm verifying the same thing. I'm doing the same thing for the second matrix, C. So with the second matrix C, what am I doing? I'm computing the eigenvalues. The eigenvectors are placed them in X and Y. And at transposing, I have a new matrix called U, which takes the transpose of the eigenvectors. And I'm performing the product U by Y to verify that I have orthogonal eigenvectors. Hello? Right. If I share the files with you, if you remember, so I place you back where we are, of those for those who have been maybe whom we have lost maybe a little bit. So we are basically Shabab in the lecture slides. Yes, Abdullah, go ahead.
Doctor, I have a question about the dot product for A transpose times A in this program. Will it give me the identity matrix as well?
I'll run the code, Abdulaziz, here. ATA, it doesn't give you the identity matrix. ATA gives you a matrix which is symmetric, whatever is A. Okay? So basically, here, we are in the lecture slides, notes. What is going on here? Okay. So we are working on the computation here done with the library on this example. So that was the matrix 3045. This is ATA, and this is AAT. We would like to find the eigenvalues and the eigenvectors and work our stuff. Okay, so just to place you back, Sharaf, in the context. So to put you back in context, so for the application screen, yes, here it is. Okay, so what else is needed, ya Shabab? What is missing right now? Once I get the eigenvalues in X and Y, for example, because it's a 2 by 2 matrix, I'm going to have what is sure mathematically is that I'm going to have the same eigenvalues and eigenvectors for AT and A. There's no doubt about it. Okay? So, but in my computation, I need to place sigma the square roots of the eigenvectors. That's why I need this line of code. You see where I'm pointing, Shabab? XS here are the no, not talk about the eigenvector. I need the square roots of the eigenvalues, because when I do ATA, I compute the eigenvalues, I have the sigma squares. I don't need the sigma squares in my factorization here, the sigmas. So that's why I need to find the squares, the square roots, sorry, of these eigenvalues. And I'm kind of doing a small manipulation to put them in a diagonal matrix. So I'm just multiplying, doing a simple multiplication of these entries and put them to obtain the sigma, the beautiful sigma matrix I need. So I'm just here, I'm not using product, Shabab, be careful, I'm using just a sample factorization, because to me, XS here would be just a column, and I'm going to multiply it just to put it in a diagonal. Okay? So finally, I'm just verifying and checking that A is equal to U sigma V. And I write this part is equal to U sigma VT. Of course, VT in my analysis here is just V, because the first V I obtained was transposed. Okay? So I can run my code, Shabab, if you allow me. And I'm verifying that the math that is processed in the slides analytically works computationally. Sometimes very important. So let's read through the output. This is the display, the printing out of the matrix 3045. This is B, which is 25, 20, 20, 25. This is A, which was obtained. This is C, which is A80, 9, 12, 12, 41. Now, for the eigenvalues, I have 445, exactly what is obtained. And these are the eigenvectors. This is the first eigenvector. It's not exactly the same one provided in the slide, but they are unit vectors. In fact, it's 1, and they divide it by square root of 2. If you want, it's almost exactly the same thing we did in the line quiz. The matrix composed of the eigenvalues, and here, as you see here, where my mouse, I'm doing the product VT times V to verify that the eigenvectors are orthogonal and orthonormal, because I got the ones here. Same thing is done for C. I mean, A times AT, you get the same eigenvalues as you can observe. Okay. If the two matrices AT and A and T are not of the same rank, I mean, of the same dimensions, of course, you don't get exactly the same eigenvalues. Part of them will be shared. The other part needs to be eliminated. Okay, and hopefully in next example, next time, we'll work on an example like this. Now, I'm verifying that the product of the two eigenvectors gives an identity. Beautiful. I'm computing XST, which are the square roots of the eigenvalues. So basically, 223 is the root of 5, and 671 almost is the root of 5. And replacing these sigmas, sigma 1 and sigma 2, diagonal of the identity matrix. So I get the beautiful sigma matrix. Now, if I do the math, the last part here, if I do U sigma times V, or VT in fact, in my case, I get 3045, which is exactly A. Hello, Shabab? Okay, any question on this? So I will upload the file also, inshallah. Right? Any question before I remove? Yes, Abdulaziz.
Doctor, could you please repeat the point about X, ST, and sigma.
Yeah, because in the sigma, I don't place the eigenvalues of AAT or ATA, because the eigenvalues that you see in mathematics, you call them sigma squares, right? So the sigma takes the root of the Hassan, takes the root of the eigenvalues. That's why I'm using the SQT function, which in fact computes the square roots of a whole array, if you wish. You get my point?
Yeah.
So in the diagonal, I have the sigma 1 and sigma 2. Hello?
Yes.
Okay, so I'll start in this. Okay, I'll go back to the slides. So today I prepared a couple of slides with you. I'll have to go through. And we start, inshallah, section 1.9, about which is a very important theme, PCA, or principal component and best law matrices. Inshallah, the slides, I will not upload them, it's not completed yet. So, but I want to run with you through this. So, because the main thing is that it gives you an idea about where we are heading. Sometimes we lose our orientation, and we want to know where we are heading. Now that we know how to get eigenvalues to perform LU elimination, CR factorization, spectral factorization, somehow this U sigma PT factorization using singular vector and singular values, so SVD factorization, decomposition. Now we want to know where we are heading. So here, this is an analysis about principal components. So let's put things in context. In fact, the principal components of A are singular vectors, okay, which we found in the previous section. So PCA stands for principal component analysis, as you see here. Uses the largest U's connected to the first U's and V's to understand the information in the matrix of data. Okay? In fact, this is the typo, being the largest functions connected to the first U's and V's. And as we said before, in fact, and one of you already answered this question, we said that it's acting as a Taylor approximation of a value function at a given point. So if you want to approximate a matrix AK, we use the singular values and singular vectors. Okay? So we said that this is acting as the best rank K approximation K. In fact, AK solves a matrix optimization problem. What do you mean by matrix optimization problem? A matrix that minimizes the distance, or that estimates the best a new matrix. Okay. In statistics, in fact, we are identifying the pieces of A with the largest values. Okay, for example, so this SVD, singular value decomposition or vector decomposition, at the center of data science. So PCA is a kind of what we call unsupervised learning, because what does SVD does? SVD gives you the most important in your data matrix. Okay, and the way to approximate it. Hello, Shabab. So to put things in context, so when the learning is supervised, we give it a different name. So people in data science, they don't call it PCA. They call it deep learning. Okay. So when we have a big set of training data, we have what we call deep learning. Otherwise, when we don't have this, the luxury of having a big data set, we have unsupervised learning. And deep learning, in fact, adds to this that it constructs a kind of a function that correctly classifies most of the training data according to their properties. So, and then we apply the new function we found to a new data to do some forecasting. Hello, for example, to give you an idea, for example, Shabab, you have taken, a set of data, collected set of data. You visited many schools, thousands of schools in Eastern province, and you collected data about boys and girls, their age, height, and weight. Okay, and you put this in data. Okay, so now you kind of have patterns. You can expect people with this age, with this height, to have this weight. Okay? You can forecast something, you do a norm, and you can also expect what is, beyond the norm, what is too much, what is too low, work on these kind of things. Okay. So we said in previous lecture that Eckart-Young, they proved that if B has a rank K, then for sure that AK, which uses the singular vector decomposition, is the best approximation of rank K of A. So whatever is another matrix of rank K, its norm, its distance from A is larger. And here we have to define what is the norm here, because there are different norms. Okay, and this is the last thing we'll see today, inshallah. So there are three choices for the norm of A, in fact. First of all, we have what we call the spectral norm, which is the A2 norm, the L2 norm, L. And what it does maximize the norm of A times X over X, and gives you this norm. We have the Frobenius norm. For those who have taken Math405, they know about Robinus Theorem. And we have the nuclear norm, a very quite fancy name here, which in fact sums up the sigmas. So in fact, it sums up the element and element here if you have a diagonal matrix. Okay. So basically, if you take, let's work a couple of examples. If you take the identity matrix of n by n, the L2 norm, what does it do? You maximize what? The norm of AX over X. Am I right? Norm of X. But since we're dealing with an identity matrix, so if you do I by X, you get norm of X over norm of X. Am I right? So basically, it's just always 1. So the L2 norm for an identity matrix is 1. Now, if you take the Frobenius norm, what does it do? It takes the, as they said here, the square root of the sum of the element in the diagonal. So basically, you have n elements, you're going to take the sum of 1 plus 1 plus 1. So you get how much? Sum of the sum gives n, so you get the root of n. While if you take the nuclear norm, you just remove the square root here. You remove the square root, so you take just, you found n. And you see just a simple case how the three norms are different. Which means that the way to measure the distance from a matrix to another, it depends on the kind of norm you're using. Okay? So you can replace also R by any orthogonal matrix too, and the norms will stay the same, which is a quite important property here we'll see with orthogonal matrices. So time is up, Shabab. Thank you for attendance. We'll continue, inshallah, next time with the content of sections 1.1, 1.9, and 1.10. Any observation, any remark before we close this? Yes, Abdulaziz, go ahead.
Doctor, I have a question about the major exam 1, when it will be, if you have any idea.
We are communicating actually with the department to correspond with the registrar to schedule it, inshallah. Okay?
Okay, thank you.
طيب. Okay, we'll communicate with you, inshallah. Okay, Shabab, thank you very much. I hope you enjoyed the online quiz 1. Even though it was scheduled Saturday night, it's kind of online homework, in fact, timed online homework. I hope you enjoyed it. I enjoyed reading your answers. Thank you very much, Shabab. And yes, Hassan, please, last observation.
Doctor, your
Hassan,
field.
go ahead.
Your field is applied math.
Okay.
I want to ask you about the math because my major is math.
I'm mainly in yeah. If you can consider it on. I'm in I'm mainly in operations research, okay, and data-driven methods in operations research, mainly on optimization with non-exact driven, data-driven methods.
Okay.
Okay, so the application are mainly on transportation and other stuff like management and engineering problems, like smart grids, data forecasting for consumption or needs in electricity for households, stuff like this. Okay, Hassan. So we'll talk later about this if you're interested. Thank you very much, guys. See you in good shape. Have a wonderful day.